Was it really sticky and wet? Was the window like on a car that it was driving and moving? But it hit the window. I don't know about y'all, but I cannot stand going into those classrooms where for some reason you touch the bottom of the desk and you got that gum that hits the desk. And what happens to it? It sticks and it's nasty to touch it. We call that inelastic collision. A tennis ball hits the wall. Well, whether you play tennis or not, if you've got it, or maybe you've played wall ball, right? And you hit that tennis ball against the wall, what happens? It bounces back. So I started off with the wall and the tennis ball, and after the collision, I have a wall and a tennis ball. So in that case, I'm going to have elastic collision. A car crumples into another car. Into, the word into is a key word there. One car crumples into another car. So in that case, I have an inelastic collision. A paintball breaks mid-air. Oh, it's better than it breaking in the barrel of your paint gun, right? But a paintball breaks in mid-air. We call that explosion. A bumper car hits another bumper car. All right, well, in that case, that's going to be inelastic collision. They don't stick together. And then the last one, it says here, I think I might need to start changing this one because it's pretty old. Morpheus and Neo run and catch each other in midair. Oh my goodness, that movie is so old, right? But either way, whether you've seen the movie or not, the key word here is each other. Okay, they catch each other in midair. So in that case, we're going to call this an inelastic collision. Okay. If we look at the example over here, I have two cars. This truck hits the back of the car, and afterwards it kind of pushes the other car away. That would be an example of a elastic collision. Also right there. So whether you see pictures or whether you get words, we need to be able to distinguish between elastic, inelastic, and explosion. Okay, let's keep going before we stop. It says here collision review. So they have the last 2 or 3 pages of what we've been talking about. They just want to kind of sum it up and review it. Elastic collisions are where objects rebound with the same speed. Okay? Now, let me stop right there because some of us are going to be like, oh no, da 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 da. Even though they use the word the same speed, let's come back over here to the soccer ball before we go any further. These 2 soccer balls were both traveling. They got into a collision because this one was going faster and it hit it over here. But if I go back and look at it, the conservation of momentum stayed the same. Even though soccer ball A came to a stop, soccer ball B made up for it because originally it was going slower. Now it's going faster. The velocity got transferred to soccer ball B, if that makes sense. Soccer ball's A velocity got transferred to B. Okay? So that's what they mean here with the same speed. It says the next one, the total amount of momentum and kinetic energy is conserved. The objects do not stick to each other, and the objects are not deformed. What do they mean by that, Miss Munson? Well, I've got 2 soccer balls over here, and after they collided, I mean, did soccer ball A and B have a big dent in it afterwards? No. If I got that tennis ball and I slammed it against the wall and then it bounced back, did the tennis ball come back all smushed and halfway in? No. Okay, so there was no deformation of the actual objects. Okay, next one. Inelastic collisions do stick together. And the total kinetic energy Actually decreases, not conserved. They're moving slower now, probably, because you got two masses together as one. And the momentum is definitely conserved. And it's the most common type of collision. Let's keep going. Next page, we have a little chart here, and they're just kind of breaking down what's going on into a chart form. We have elastic and inelastic. No, they haven't. No, they don't have explosion on there. It's like the opposite, right? So elastic collision is conserved for momentum. The kinetic energy is conserved. Somebody or both of them are still going to be moving quite fast. Deformation, no, not really. It's going to occur. Stick together, no. But inelastic collision, momentum is still conserved, but kinetic energy is not conserved. And deformation normally occurs, but sometimes it may not. But most of the time it does. And yes, it sticks together. Okay? So remember that the momentum is before a collision is equal to the momentum after. And because of that, we can say that P before equals P after. Okay? So to find the momentum before, we must find the momentum of each piece before the collision and add them together. Okay? So in this case, my equation that we're talking about, or what we're talking about, because we're about to make a new equation, is P before equals M1V1 plus M2V2. This may not make a lot of sense right now. It's a new equation. I will talk about it in class. So to find the momentum after we must find the momentum of each piece after the collision and add them together. And so in that case, my equation is going to be, I'm going to put an arrow here, I'm going to put an arrow here. P after equals M1V1 plus M2V2. Now, let me try to explain this. The P stands for momentum, so the momentum before the collision is, for an example, the mass of object 1 times the velocity of object 1 plus the mass of object 2 times the velocity of object 2. And the P after, because those two should equal each other, I should be able to set them equal to each other, is the mass of object 1 plus the velocity of object 1 plus the mass of object 2, times the velocity of object 2. I'm sorry, I said plus. I meant to say multiplication. Now, those two equations we actually did over here, but we broke them down piece by piece for you. So our new equation that we're going to come up with, and let's look at this equation. A lot of people are like, are you serious? And yes, I am serious. This is our equation here. Let me see. Can we see this? That's kind of a light color. Here, we'll go with the dark green. Here's the equation. Don't freak out. M1B times V1B plus M2B times V2B equals M1A times V1A plus M2A times V2A. And that's only if I have two objects. If I have three, I keep going. If I have four, I keep adding. If I have six, they all better be here. Okay? We have to account for every single part. All right? So let's go over what they mean to make sure that we understand. All right? M1. I don't care if you have M1A or M2A. And I'm going to put here A or B. Okay? M1B, M1A. I don't care. But they're going to be the same. And it's the mass of object number one. Before or after. It's going to be the same. V1B, though, stands for the velocity of object number one before the collision. M2, again, I'm going to go ahead and put A or B, parentheses, because I don't care if we're talking about M2B or M2A. We're talking about the mass of object number two. And they're going to be the same. Are they always going to be the same? I mean, for us right now in high school physics, yes. I don't know about you, but when I'm walking and I actually bump into a table or chair, I don't lose weight. I mean, if that's the case, well, heck, I would be bumping all over and running into the wall and everything. But when I'm walking, I don't just hit something on accident and then now my mass has changed. No, that would be too easy. My mass, all my weight stays there. It doesn't shake off or anything. Okay, but V2B is the velocity of object number two before the collision. V1A is the velocity of object number one, V1A, after the collision. And then V2A, that velocity of object number two after the collision. Okay? And then again, though, if we have three objects, it's going to be three. If we have four objects, it's going to be four. So here is that equation from up here. But there's a problem. The problem is that we actually need to modify this equation based on each situation from the problems that you read. Okay? So when we read it and we find out that we have an inelastic collision, we need to change this. If we read the word problem and we have an explosion collision, we need to change that. Okay? So here is my base equation that I'm going to start off with, but I have to manipulate it and change it due to the amount of objects that are in the collision as well as what type of collision that I'm having. Okay, and we will definitely talk about that in class because this is probably one of the most confusing questions and how to solve it. And it's not on the formula chart. You need to understand it so that way when you're taking your quiz and test, you can manipulate this equation for you. Okay, other than that, I'm going to pause here. Go ahead and give me a moment to upload these video notes and then you'll have them as well. All right, have a good day.